Dear guests, today I'm going to present you benchmarking multi-instance learning for multivariate time series analysis for the workshop. So first of all, I would like to give you the overview of the presentation. So today we are going to talk about time series analysis, multivariate time series classification, multi-instance learning framework, multivariate time series in the ML framework, and the results that I have obtained. By the way, my name is Rufat Babayev from Fraunhofer Institute of Toxicology and Experimental Medicine. So what's time series analysis? So time series analysis is a series of data points indexed or listed or graphed in time order. So time series analysis comprises methods for analyzing time series data in order to extract meaningful statistics and other characteristics of the data. For example, monthly sales at a souvenir shop, stock price of a company over years, server overload data through months, heart rate of a patient during a day, and other types of analytics data. So there are like two types of the time series data. One is the univariate time series data, which contains measurements of a single variable collected over time. For example, number of passengers using a subway in a town through years, for example, might be the univariate time series. And there is also multivariate time series. So multivariate time series contains measurements of multiple variables collected over time. For example, an hourly measurement of systolic blood pressure, heart rate, respiratory rate, albumin level, and pH level might represent a multivariate time series, as you see in the image. So what's the multivariate time series classification? So the time series classification deals with classifying data points over time based on its behavior. In that manner, multivariate time series classification deals with multivariate time series data. So here we have the multivariate time series. So that contains like multiple univariate time series with m dimensions, and it passes through the neural network in this example, and then the probability distribution over k classes is generated. So now I would like to talk about the dataset that I have used. There are publicly available medical datasets for multivariate time series classification. Two of them are physiognomic tree. They are fairly complex, having high missing rate and unequal lengths time series. So in this case, we selected the PhysioNet dataset. So in this dataset, it records the multivariate time series of 48 hours after the intensive care unit admission of a certain patient and contains 36 variables, such as mean arterial blood pressure, heart rate, respiratory rate, etc. Dataset is divided into three sets: set A, set B, set C, each having 4,000 multivariate time series. Set A and set B is used in our evaluation. And we actually performed the mortality prediction task on this data set to predict whether a patient dies in a hospital after 48 hours. So there are two classes. One is the positive class with a level of 0, which represents a dose, and another one is a survival with a level of 0. And the class imbalance for each of these is roughly 14% to 16%. We do a random undersampling to make a balanced data set. And a mean and forward imputation is applied to this dataset as well. So around 80% missing rate is present in the dataset. So multi-instance learning is a type of supervised learning where the data points are collected in multisets called bags, where the entire bag has a label, either a discrete or a real value. To the data points of each bag are called instances. For example, here in this picture, we have like future vector instances, like data that are present in the traditional data. We collect them inside the bag, we pass it through the MIL classifier, and we have the classification prediction at the end. So main purpose is to learn a model from the instances of a bag and the level of the bag, such that a bag level and instance level predictions can be generated. Our focus here is more specifically the binary classification task. So to solve this problem, we consider two assumptions. The first one is the standard MI assumption. It considers if all instances inside the bag are negative, then the bag level is negative. If one of them is positive, then the bag level is positive. The collective assumption considers a bag B as a distribution P Z B, probability of instance Z given a bag B over the future space Z. Similarly, considers labels as a distribution PCZ over instances, where class C is a class from 0, 1, Z is an instance in a future space Z, and B is a bag. So the collective assumption then models the distribution as follows. So PC given B, the integral for over the future space Z, PC given Z multiplied by Z given B dZ. So in this formula, the probability distribution PZB is not known. Hence, the empirical version over the instances in the bag is calculated as shown in this formula, where MB is a number of instances inside the bag. Since PCZM is also not known for all M from 1 to MB, most methods based on the collected assumption learns this distribution as in a single or traditional data set. Finally, the bag level of a bag is determined by P hat C equal to 1 given B, or P hat C equal to 0 given B. So if one of the probability is higher, then the label of a class is determined by that probability, basically. So how the multivariate time series is represented in MIL framework, it is actually so we have the multivariate time series xn and the observation of all the variables at each time step t from 1 to tn as an instance of this bag. More formally, the bag bn of xn is defined as bn x1 x2 up to xtn, where the class level of xn becomes the bag level of bn. So with this in mind, various multivariate time series having different lengths can be considered in their own encapsulating bags. So expressiveness of the original values is maintained without rescaling the time series data. Now I would like to show you the results, like how multi-instance representation of the multivariate time series is actually learned by the multi-instance learners. So we use multi-instance learners, and as I said, we have like 3 sets, set A, set B, and set C. Here in this table, we have set A as a training set and set B as a test set. So MILR is multi-instance logistic regression. The bagging MILR means the bagging combined with MILR. And so the purpose of using bagging and boosting, such as relatables, is to get rid of to handle the overfitting or underfitting cases for our learners. So multi-instance wrappers are used to wrap the multi-instance data or convert it to the single instance data and run it with the, for example, here with random forest. And so on and so forth. So here, as you see, so for example, this configuration means the relatables wraps. So the multi-instance data is wrapped with multi-instance wrapper. The classification is performed on the random forest with forward imputed data, and spread subsample class from WECA is used to randomly undersample the data, and then the classifier is again wrapped in the relatables to improve its performance. Here, as you see, so this all the configurations above this point are actually the multi-instance learners. This the last 2 configurations are the ones that we convert the data time series data to the traditional data by averaging or by finding a mean of certain dimensions in the time series data. So we only see that like the RB, MIW, RFFSS is performing closely to the averaging configuration, but not better than the averaging configuration. We also had the results for the cross-validation, but still, so this configuration was outperforming this one, but still there is an expectation that we can get an improvement. So I discuss it in the next slide. So to improve the classification of the multi-instance learners, so we can weight the instances inside every bag differently. So to use a weighted MI assumption. So here, for example, when we go back to the to this probability distribution, we might have the some weight multiplied by PCZM. So this is one possibility. Another possibility is, so here we have the proportionalization of the multivariate time series data, but this is a very straightforward method. So maybe we can have more sophisticated way of proportionalizing the time series data, for example, by random forest and so on. So these are the like main directions for the future work. And yeah, that's it. So if you have any questions, just I am here to, I will be happy to answer. Thank you.